Hello everyone, let's solve few more problems on DBMS. So let's solve the very first problem in which a relation R is given, which is having PQRST attributes, and these set of functional dependencies are also given. And here it is being asked that how many of the functional dependencies violates the 3NF. So if we want to check the 3NF, there are two conditions. The very first thing, if I write X implies Y, in this X has to be a superkey. Second, if X is not a superkey, then Y need to be a prime attribute. Right? So the very first thing we should do it here, that calculate the possible number of keys which this relation can have. So if we consider, let's say, whether P can be the key. So if you calculate the closure, find out the closure of P, it will give you PQ and nothing else. So that means P cannot be the the key. Then if you calculate the closure of, let's say, Q will not give you anything, so Q can also not be the key. Now let's say if we take the closure of R will give us R and S, and R and S collectively doesn't give us anything, so this is also not the key. Similarly, if we set T, the closure of T will give you T, R and S, but it cannot generate P and Q, right? So T can also not be the key. Now we need to try the combination of two. So let's say if you try PQ, the closure of PQ will give us PQ and nothing else. So PQ cannot be the key. Now let's try another combination with P. So let's say if we try PR, so the closure of PR will be PR, and P can generate Q, R can generate S, and Q and S collectively can generate T. So that means PR is capable to become a key, right? PR is capable to become a key. That is fine. Now if we perform or write P combination with, let's say, S, so it will give us PS. Now P will give us Q because P implies Q is already given. Now PSQ collectively, SQ can give us T because QS can derive T, and T can give us R. That means PS can also be a key, right? Then let's try PT, whether PT can be a key or not. So PT will give us PT, and P can derive Q, and T can derive R, and R can derive S. So that means it is also capable to derive every attribute of the relation. That means PT can also be the key. Now if you try any further combination, like if you try QR, if you do not include P, because P is a prime kind of attribute, you will not be able to generate P. So if P is not there, this cannot be the key. You can easily check it. So this cannot be the key. Now if you check RS, again P is missing, So rest of the combination without P, it is really difficult. I mean, in this situation, the key cannot be decided without including P. So these three are the candidate key, or you can say key, right? So that means you consider P, R, S and T. P, R, S and T can be considered as prime attribute, right? Now let's check the functional dependencies one by one. So if we check the functional dependency, like the very first, P implies Q. P cannot be the key, it is not a key. Then Q has to be the prime attribute. So whether Q is a prime attribute, because P, R, P, S and P, T are the key, Q is not the part, so that means it is not the prime attribute. It violates the condition of 3 and F. So one rule is violating, then another, let's say R implies S. R is not the key, but S is the part of key, so you can say S is a prime attribute, so it does not violate. Then QS implies T, the third dependency. QS cannot be the key, but T can be the prime attribute, so it does not violate the condition of 3 and F. Then the last functional dependency, T implies R. T cannot be the key, but R can be a prime attribute like this, so that means it does not violate the condition of 3 and F. That means we are having only one such rule which is violating the condition of 3 and F. So the answer should be A only. So let's discuss next problem. In this problem, there are two statements are given. One is saying canonical cover of a set of functional dependencies may not be unique. And second is saying there is a functional dependency set given, and they are asking the canonical cover of this FD set is unique or not. So what is the canonical cover of set of functional dependencies? Actually, when a set of functional dependencies are given, sometimes few of the functional dependencies may be redundant, or any of the portion of the functional dependencies may be redundant. Like if I'm saying AB derives C, so according to the further given functional dependencies, this rule may be redundant. The meaning is, if we do not consider this rule in the given set of functional dependencies, whether all the things which we were earlier able to find out, we can still able to find out, then this functional dependency will be treated as redundant and we can remove it. So what is the canonical cover? It is the minimal set of functional dependencies which will be equivalent to the given original set of functional dependencies that we consider as the canonical cover. So let's check how we can find out the canonical cover. And remember one thing, canonical cover of a set of functional dependencies may not be unique. It is true. We will see it even by solving this problem also. So please do remember that when a functional dependency set is given, the canonical cover for a given set of functional dependency may vary, or one set of functional dependency may have more than one canonical cover. So it is not necessary that the canonical cover will always be unique, right? So the first statement is true. Now let's check the second one. Second one says this functional dependency, we need to find out the canonical cover, okay? And then we can find out whether it is unique or not. So the very first functional dependency, and PQ implies R. Next is P implies Q, and next Q implies P. Now we need to find out the redundant thing. So how we can find out the redundant thing? Let's say we are trying to find out whether the very first rule is redundant or not. So what we will do here, we check first thing, the closure of PQ. Let's say if we find out, we will get PQ and R. PQ can drive R, right? When we are aware about P, we can get Q and so on. So that means PQR we are able to find out. Now the next thing is, if we do not consider this rule, so I'm considering this rule is not given. You are having the remaining thing. And now if we calculate again PQ closure, now you check what we are getting. P can give you Q, so let's say PQ, you are already aware about, Q can give P. So that means we will not be able to find out R. The meaning is, once you do not consider this rule, you will not be able to find out some attribute like R. That means this is one of the essential kind of functional dependency. So that cannot be removed further. So this PQ implies R cannot be removed, but we can check whether some of the portion of this functional dependency is redundant or not. So the meaning is, portion means if I remove from left hand side, let's say P, if I remove, and if I just write Q implies R, whether we will get the same thing or not. Okay, so let's say we consider the closure of PQ, and PQ closure we are having P, Q and R. Now if we do not consider this P and we just have Q implies R and rest of these two rules. So let's find out the PQ closure now. In the closure of PQ we have PQ, fine, and Q can give us R. That means the same thing, we are still able to get it, although if we can neglect Q here. So that means P here. So this P is redundant. Whether we write it here or not, it does not affect. Right? So instead of writing PQ drive R, we can write Q drive R. Q implies R. Okay? Now you check the next case. Let's say if we consider only P is deriving R, Q is redundant. This time I'm considering Q is redundant. And rest of the two functional dependency, P implies Q and Q implies P, is given. So if you calculate now the closure of PQ, you will find out PQ, and because you are saying P drives R, so you will get R. That means the same thing you can get even though you don't have Q here, you just have P implies Q. Okay, P implies Q cannot be removed because let's say if you have here, so if you find out the closure of P, P closure will give you P and it will give you Q, and PQ can give you R. So if you remove this rule, and if this rule is not given, if you now try to find out the closure of P, because there is no rule given from P, you will be only able to get P, because if this rule is not given, then nothing you can derive. So that means this is one of the essential rule. This P drive Q is one of the essential rule. Now let's check whether the last rule we can remove or not. So in last rule, we try to find out the closure of Q, and Q will give us Q, and Q can drive P, and PQ can drive R. That means all. Now if you do not consider this rule, Q implies P, and now if you calculate the closure of Q, you will be able to drive only Q, nothing else, because this rule is missing, we are considering. So that means this last is also essential. It is also essential functional dependency. We cannot remove it. So what will be the canonical cover now? Canonical cover is the minimal set or optimal set of functional dependency which will be equivalent to the previous set. So I'm writing here, either we can write the canonical cover. So I'm saying canonical cover like CC, 1 CC. The very first possible canonical cover can be P implies R, P implies Q, and Q implies P, right? Another canonical cover we can write like this, when Q implies R, P implies Q, and Q implies P. So there are two canonical cover or minimal set of functional dependencies are possible, which is equivalent to the original functional dependencies. Okay. So we can combine like this thing, P can drive QR, we can write simply, and here we can write Q drive PR. Okay. So this thing can be written like P implies QR and Q implies P. This thing can be written as Q implies PR and P implies Q, right? So this is the canonical cover of the functional dependency. Now let's read the statement. S2, canonical cover of FD is unique. No, there are two possible canonical covers, so that means it is false. So the very first one is true and second one is false, that means answer will be C. Now let's look at the next question. Consider the functional dependency set on a relation R1 which is having three attributes P, Q and R. And these are the functional dependency. P implies Q, R, P implies Q, Q implies R, and PQ implies R. The canonical cover again we need to find out. So let's find out the closure of this. If we find out the closure of, let's say, P. So if we write the closure of P, P can get P and it can drive QR. So that means all three attributes can come in the closure of P, right? Now if you do not consider this P implies Q, R, P implies QR, if you do not consider, then can you drive the same thing? So if this rule is not there, rest of the functional dependencies are there. If you calculate now the closure of P, you will get P and P can drive Q, so you will get Q, and Q can drive R, you will get R. That means if you ignore this very first rule, then still you are able to generate the same thing, right? So this rule can be neglected or will not be the part of canonical cover. Now same thing is applicable for another. We need to check this thing. So if you check this thing, P implies Q, so because the options are given very fixed, so you check P implies Q whether it should be the part of this. So if you find out the closure of P by having this P implies Q, it will give you PQR. But if you do not consider this rule, then the P closure will still give you PQR. If you have this rule, then this will give you PQ and R, right? So if you don't have this one and if you don't have this one, then the P closure you will not be able to find out all, right? P closure will have only P in that case. Okay. So P implies Q cannot be removed because we have already removed this rule. So because we have already removed this, we find out this rule as redundant. So we will not be able to find out P implies Q as a redundant rule, right? Now let's check for Q. So if you try to find out the closure of Q, you will get Q, R, So Q will give you QR, and that's all. So it will give you QR only. But if you remove this rule, and if you want to find out the closure of Q, if this rule is not there, Q implies R, in that case you will not be able to find out QR in the closure of Q, right? So that means this is also essential, you cannot remove from the canonical cover. Now let's check for PQ implies R. So if you check for PQ implies R, the closure of PQ is PQR. But if you do not consider this rule, let's say, then remaining two rules can drive this thing or not. So if you calculate the closure of PQ now, it will give you PQ, and here P can generate Q and Q can generate R. So that means you will get R also. The same thing you are getting even though you have not considered PQ implies R. That means it is redundant. So this is also I am crossing. Now what they are asking, the canonical cover of this set is, canonical cover of this set is P implies Q, Q implies R. That means A will be the right answer. Okay. Now the next question, if a relation this R, which is having W, X, Y, Z, has no non-trivial functional dependency. Okay, so we have already discussed the meaning of non-trivial or trivial functional dependencies. So trivial functional dependencies, which is obvious thing. Non-trivial means which is not obvious. If it is not given, we cannot predict that, right? So trivial means if you say A implies B or A drives B, then B must be the subset of A only. That is trivial. Right? But if no further non-trivial functional dependencies is given, that means no attribute is capable to derive any other attribute or able to identify the other attribute. If anything such given, only the trivial dependencies are there, no non-trivial dependencies there. In that case, when we want to set the key, all the attributes of the relation should be the part of key. If all will not be able to be part of key, then we will not be able to find out all the attributes of the relation. I hope you are getting. So if W, X, Y, and Z, they don't have any non-trivial functional dependencies, that means key need to be W, X, Y, and Z. If any attribute you will miss in the key, then you will not be able to drive that attribute because there is no other non-trivial dependencies given, right? So for this relation, candidate key should be W, X, Y, Z. Individually W, X, Y, or Z cannot be the candidate key. Even the combination of 2 will not be the candidate key. So the answer will be A only. Consider the following instance of a relation R1, and the instance is having P, Q, R attributes, and the values are given for P, Q, R. Now what is the number of functional dependencies in the canonical cover of this instance? So let's find out the very first functional dependencies. If I say whether P implies Q exists here or not, let me verify. So P is having 1 association with 10, 1 association with 10, 2 associated with 10, 2 associated with 10. So that means this exists. Now if I say P implies R, let's verify P implies R exists or not. Here 1 is being associated with 100. Now this one is associated with 200, so there's a problem. That means it doesn't exist. Now let's check Q implies R, let's say. So Q implies R. Now in Q implies R, 10 is associated with 100 and 10 is associated with 200, so it does not exist. Then let's say Q implies P. 10 is associated with 1, 10 is associated with 1, 10 is associated with 2. No, there's a problem. So it does not exist because different association is not allowed. Then let's consider R implies P. So check R implies 100 to 1, 200 to 1, 100 to 2. There's a problem. 100 and 100 here and 100 here having two different association. One is with 1, another is 2, so it doesn't exist. Now let's check for R implies Q. R implies Q 100 to 10, and there is also 100 to 10 association is there. That means it is fine. It's not a problem, right? So invalid I'm going to remove. This doesn't exist, so I'm removing. And the very first one is also does not exist, so I'm removing it. Now let's see in the combination if anything exists. So if I say PQ implies R, whether it exists. 110 is associated with 100 and 110 associated with 200, so that means it doesn't exist. Let's check for another. So let's say if we are checking PR implies Q. Now PR means 100, 100, then 1, 200, then 200, and then 2, 300. That means all combination of P and R will be unique. If all are unique, that means it will be valid, it will exist, right? So 100 mapping with anything, it doesn't affect. Then 1 and 200, 2 and 100, and 2 and 300 all are unique, then it will exist, right? So I will wipe it out and these three are valid. Then let's check for further. You may be interested to check QR implies P. So let's check. Now Q and R, 10 and 100, 10 and 100, and they are having two different association, 1 and 2. So that means it doesn't exist. So overall you can say these three functional dependencies are valid. Okay. Now for these functional dependencies, we need to find out the canonical cover. So what is the number of functional dependencies in the canonical cover? So if we find out the canonical cover of this, P implies Q, R implies Q, and PR implies Q, you can easily find out. You can usually find out that which rule is redundant. So if you consider the very first thing, if you calculate the P closure will give us PQ, P closure can give us PQ, right? And if we do not consider this rule, then without this, if we calculate P closure, we will not be able to find out PQ. So that means this is essential. It will be the part of canonical cover. Same thing if you calculate R closure will give us RQ, right? R closure will give us R and Q. If you do not consider this rule, if you calculate the R closure, you will not be able to find out RQ. So that means this is also essential. RQ is also the essential and it will be the part of canonical cover. Now let's check PR. So PR, if you check, PR will give us PRQ. And if you do not consider this rule, and if you calculate the closure of PR, still you will get PR, P can drive Q, so that means you can get PQR, the same thing which you were getting this, even though you are not considering this. So this rule will be considered as redundant. You can remove that. So that means canonical cover will have only two functional dependency, P implies Q and R implies Q. So that means they are asking the total number of functional dependencies. So the answer will be two functional dependencies are there. I hope all these questions are clear. Thank you everyone for connecting. See you in the next session.